Dear students, in this video, we are going to learn about counter propagation networks and, and adaptive resonance theory. Okay. So the CPN was artificial neural network, which is consists of both the supervised and unsupervised. It was introduced by Robert H. Nielsen in 1987. It consists of two layers. One is Kohanen layer, which is unsupervised, and Grossberg layer, which is supervised. So how exactly it works, we'll see. So coming to the first layer, we'll have the input layer. Second one is Kohanen layer. Third one is Grossberg layer. So Kohanen layer is an unsupervised, which is exactly what we have learned in the SOM. So it will have all the set of 2D vectors, and according to the code book, you have to update it and you have to get the output, and you will convert into clusters because we will calculate the distance between the 2 points and we will set whether this belongs to which particular cluster. Coming to the second one, Grossberg layer, output layer. This layer maps the cluster from the Kohanen layer to desert output using supervised. Suppose if I'm creating two layers, okay, better I'll explain you 1 second. Yeah. So if you closely observe here, I'm taking some input. So I'm taking some set of points. You know that how the values will be there. Suppose if I have x1, x2, okay. So here you'll have x1, x2 or x2 comma some value. I'm just writing the values and x3 comma some value, some new decimal values 4. Now in the first, this is your input layer. I'll substitute this one into Kohanen layer. Okay. So it will give some clusters over here. So it will say that this x1 will be here, x2 will be here, and the distance between the matching is less, or it will not belong to this particular code vector. Then what I'm doing, so here I'll form two clusters. Okay, suppose this is C1 and this is T2. I'm drawing the line over here. And this is an unsupervised learning. I don't know whether it is correct or not. I'm only finding the matching between two things. And the next layer is your output layer. What you are going to do here is already have the T1 cluster and T2 cluster. So I'll take these two cluster and I'll, according to their output, whether C1 belongs to T1 or C1 belongs to T2. So, C2 belongs to T2, or maybe C2 belongs to T1 or C1 belongs to T2. So this will be of the supervised learning. So you'll have the supervised, means you'll have the target values. So what is the basic structure of this one is first you'll have the input. Second layer is Kohanen layer. Third one is, and this will be done with the help of SOM, self-organizing map, and output will be supervised learning with the help of the given code vectors. So this will be exactly happened in your algorithm, which we will going to see now. Okay, so this we have done. Okay, it will be operates in the two phases working principle. First one is Kohanen layer training, unsupervised learning. According to that, we'll initialize the vectors and neurons randomly, and you will present input vector to the network. And best matching unit, what we have done in SOM, it will calculate the distance between the two closest input vectors with the help of the Euclidean distance. And if you are not able to properly find out this particular distance, we have to update the weight according to the BMU. And this will be done at the training phase of this particular SOM. Second one is Grossberg training layer training, where you'll have the target vector. We'll present the target vector for the input vector. If target vector and the input vector are same, so we'll stop here. Otherwise, again, I have to adjust the weight connections between BMU to the Kohanen layer and Grossberg layer to minimize the error between actual output and the target output. So this is your phase 2. Then third one is your recall phase, where present a new input vector and will identify the BM, and I will identify the output generation. So same thing, all this will be done. Okay, we'll see with one example. So here we have the 2D input vectors. These are the values, and T is your target vector. Remember that this target vector is only used at the output layer, that is Grossberg layer. Okay, in the Grossberg layer, not in this Kohanen layer training. Okay, because Kohanen layer training is unsupervised part. Now, initialize the network. We'll have this one train the Kohanen network, Kohanen layer with the help of these weights and T neurons. And what are the initial weights? When the when the input vector is 0.1 comma 0.1 comma 0.8. So which one is the best match for these two? So I'll calculate the Euclidean distance between these two and these two. Okay, after getting the best match, you have to train with the BMU with the Grossberg layer, and these two best match will be identified with the target vector. If both are equal and it is best within the target vector, I'll stop. Otherwise, I have to change the weight layer. So recall phase after training, we have to add a new input vector for that. So this is the testing phase. Okay. So if anything is here, if I'm not able to train coherent layer, I have to adjust the weights. If I'm not relate according to the target vector, again I have to change the weights accordingly. Okay, so till Grossberg layer, it is a training phase, and recall phase is the testing phase where I can add a new, okay, present a new input vector which can be trained accordingly. So what are the different applications for your Cohen? This one, okay. So classification, we can easily classify the points, function approximation, data compression. So as we are using Cohen layer, compression will be obviously applicable for that. And approximation, because we are using the distance vector or Euclidean distance formula, we can use both for the function approximation and classification. So we can use the clustering for dividing into group of clusters, which will classify into the clusters. Now, what are the advantages? The first one is hybrid because it is adding both supervised and unsupervised. It is more efficient because we are using Cohen layer as it will reduce the dimensionality. And the disadvantages, complexity, because you are combining both unsupervised and supervised. It will be very difficult for implementation part, and initialization sensitivity, because always the final result will depend upon initialized weights and learning parameters. Finally, CPN are effectively for function approximation and compression, all these things. And if you remove all the disadvantages, this will be the best networks for your any of the complex problems. Now, next one is adaptive resonance theory. It is the family of neural network given by Stephen Grossberg and Gail Carpenter. It is designed to solve stability plasticity dilemmas, ensuring the new learning does not disrupt existing knowledge. So these models are mainly used for pattern recognition, clustering, classification, where input data is noisy or non-static, that is non-stationary. So what are the key concepts? First one is stability, plasticity, dilemma. Second one is vigilance parameter. So these are very important terminology for art. So please do remember all these terminologies. So what is plasticity or stability is challenge of learning new information is called as plasticity without forgetting the previous information. See exactly what we will do. So when we are going to learn the unit 2, you will forget unit 1. So that you should not do. So when you learn new things, that is plasticity, you have to remember the old one also, that is stability, that is previously learned information. And vigilance parameter as threshold that determines the level similarity required for the new input belonging to the existing cluster. Okay. So best example, if I'm learning new thing, it is plasticity. If I'm not forgetting old one is, that is stability. So what is the difference between how to control these two? What is the main thing? What is the parameter required in order to maintain the balance between these two values is called the vigilance parameter. So what are the different models? We have Art1, Art2, Art3. So Art1 is adaptive resonance theory. One deals with only binary input patterns. Second one deals with continuous. And third one, it will add more biological realism to Art2 by incorporating complex mechanisms of synaptic plasticity and the other neural process. So what is the Art3 will handle continuous input plus biological representation of neurons, that is synaptic plasticity. So we'll just see the Art1 architecture. So Art1 will work only with the binary input vector. So it will have the first layer as the input layer, F1 layer takes a binary input. Second one is the recognition layer, consists of nodes that represent cluster of inputs. Gain controls ensures that input is properly normalized and flow of activation between the layers. Fourth one is your comparison and matching, compares the input pattern with the stored recognition patterns. Finally, it is vigilance test. What is the parameter required in order to balance the already learned one and what you are going to learn. That is plasticity and stability. So the learning process will consist of the following phases. One is initialization, input and compute the similarity pattern matching between input vector and each prototype. So initialize the weight and set the vigilance parameter. Present a binary input vector to the F1 layer. In the pattern matching, you have to compute the similarity input vector, each prototype with the help of the weight vector in the F2 layer. So this is winner takes all strategies, means how much points you're getting more, those people will be the winners. Now, what is vigilance test? If the similarity of the both already learned one learned winning neuron is okay, it is according to the threshold, then we won't change anything, but it is above the vigilance threshold, you have to update the weight. If the similarity is below the threshold, temporarily inhibit winning neuron and repeat the pattern matching with the next one. Okay, so this is in two cases. It is above the winning neuron, you have to incorporate new input pattern. If it is below the winning neuron, you have to repeat until if you get the similar prototype. Learning, adjust the weight to the selected neuron to move closer to the input pattern. And this process will be repeats unless until all the vector system is stabilized. So we'll see one example. So here I have a binary example, x1 and x2. So in the initialization, I'm initializing F2 layer are randomly set to small values and vigilance parameters is 0.5. So present the input pattern, that is x1, compute the similarity for each prototype in F2, that is x1 to F2 layers. Check the similarity, whether it is exceeding the vigilance parameter. If not, you can go for the current prototype, otherwise, and try next one. If the vigilance criteria is met, update the weights to the selected and incorporate x1. Repeat the process for x2 and additional input patterns. So this is a simple algorithm where we are going to use both the layers. Okay. So where we are going to apply this, same as it is, pattern recognition, clustering, anomaly detection, and data compression. Why anomaly detection? Because we can identify the unusual patterns which are existing in the networks. Okay. Clustering, group of similar points can be clustered. So you can remember the stability that is already learned one. We can compare with the new learning technique for the pattern recognition. And finally, data compression. So this is a final one. So what are the advantages? It will be an incremental learning. It can be used for real-time learning and robustness. And what are the disadvantages? Very complex and vigilance parameter have to be identified properly. Otherwise, it will like dilute whole network. Finally, it is a robust framework for unsupervised, addressing the learning and ability thing over here. And it is well suited for recognition, clustering, and anomaly detection. So this is related to your CPN and ART. Thank you.